Hi everybody, and welcome to Engineers Week. We're so happy to have you, and we're really happy that we were able to put on this program this year. So welcome, my name is Sarah, and I'm a civil engineer who works here in Peoria. And as you can see behind me, the thing that we're going to talk about today is bridges.
Think of how many bridges we use every single day. They're everywhere. They let us drive our cars over the Illinois River or over the highway, and in general, they open up places to us in the world that we wouldn't be able to reach without them. Bridges have been around for centuries, and the first bridges were just as simple as putting a log over a creek so that you could walk across it. But since then, bridge design has evolved into so much more. And even though these designs have become more intricate and more complicated over time, they all serve the same ultimate function: to take the forces of a heavy load, such as a person or a car, and then transmit that through the bridge and into the abutments, and in this way, the bridge stays up. I realized I used a technical term there. Abutment means the parts of the bridge on either side of the thing that you're crossing, and they're really big, usually made out of concrete, and they bear the entire weight of the bridge on either side of the thing you want to cross. Bridge design can be broken down into a few major categories like an arch, suspension, cable stay, and beam bridges, but today we're just going to talk about the most common type of bridge, the beam bridge. But first, before we can talk about that, we need to talk about what makes a bridge stay up, namely the two major internal forces in a bridge, tension and compression. So tension is a pulling force, and compression is a pushing force. And when these two forces work together, you can create a bridge that will carry a load. So let's talk about the relationship between tension and compression forces and loads. Look at this slinky. If I push or pull it apart, I'm exerting a sideways load on it by pulling it in tension or pushing it in compression. I can feel the slinky resisting me a little bit, but the slinky's still really flexible, so it moves around a lot. And I can't put much of a downward load on it without it falling down. So I wouldn't want to cross a bridge made of slinkies. But what if we scratched the slinky idea and we tried using a material that was a little bit stronger? You can see that some bridges are made out of concrete, and concrete is really good under compression, but it's not so great in tension. Concrete is made up of sand and mortar is basically a glue that binds all the sand together. And just like when you make a sandcastle, it's a really good material for taking squeezing loads on it or compressive loads, but it's not so great in tension. So sometimes when you see concrete used on the deck of the bridge, which is the freestanding part, you can assume that concrete has been reinforced on the inside with steel bars to make it stronger in tension. That brings us to the other type of common material that's used in bridges, and that's steel beams. Compared to the slinky, steel beams are kind of like a pencil. If you take a pencil in your hands and you push it together just like we did on the slinky, it stays strong. And now if you try to pull it on each end, it still maintains its shape. Steel is like this in that it's good at taking both tension and compression forces. So let's talk about beam bridges. These bridges are some of the simplest designs, a relatively short, straight beam over two strong abutments. All bridges have two types of loads that they have to carry. Cars and people that exert a load on the bridge are called dynamic loads because they can move around, and then it also needs to carry its own weight, which is called the self-load. And in a simple beam bridge, you only have this one beam that's supported by these two edges. So anytime that you have a load on it, that load needs to travel horizontally through the beam to the bridge abutments, and then all of the weight goes down through the abutments and into the ground. And this is how a beam bridge stays up. The top of the beam shortens a little bit, which is called being in compression, and the bottom of the bridge stretches in tension. Because nothing supports the bridge in the middle, the simple beam bridges are only good for relatively short lengths because you don't want to put a bunch of load in the middle and then have your bridge sag with nothing to support it. So a way to get around this issue is that we can build a special kind of beam bridge, which is called a truss bridge. And a truss is basically a bunch of connected small segments of beams over your main beam, which is the deck of the bridge. And the way that the truss works is that at every point that's connected to the deck, it will pull up a little bit and relieve some of the tension on this deck bridge. So instead of just having your bridge supported on the two sides like in a simple beam bridge, the bridge is actually being supported throughout the entire length of the bridge. So some truss bridges have the truss over the top of the bridge, like the Murray-Baker Bridge, and some trusses actually have the truss placed beneath the bridge. But no matter where your truss is placed, it helps support the beam from along the bridge deck and uses the tension and compression distributed throughout the various beams of the truss to spread the forces along the beam so no one area bears too much of the load. One other thing to consider is that the shape of the truss actually makes a difference. Sometimes it's hard to tell just by looking at a truss which beam segments, called members, are in tension and which ones are in compression. Although every truss design is different, you can generally assume that just like in the slinky example, the members at the top of the truss will be squeezing in compression and the bottom members will be stretching in tension. Engineers can do calculations to find out exactly which beam segments are in tension and compression and exactly how much force each member is carrying, but we don't really need to worry about that too much for this activity. In this activity, we're just going to try to build our own truss bridges, and we're going to see how building a truss actually makes a beam so much stronger, and how when you build a truss, even out of a weak material like spaghetti noodles, you can carry relatively a lot of weight before your bridge breaks. All right, are you ready to give it a try?
We're going to need a few things to build our bridge. You will need dried spaghetti noodles, mini marshmallows, a printed out template of your truss, which I provided on the website, or if you want to draw a sketch of what you want your own truss to look like, you can do that. Just make sure that the bottom length is 10 inches, and that's already set for all of the pre-printed trusses.
Now that we know what we need, let's get building. The first thing that we need to do is pick our truss design. You can either use one of the pre-printed designs that I provided, or you can make your own. If you make your own, just remember that the bottom length needs to be 10 inches, and also you want to put a flat top on your design, so no arches on the top. This is because it's just going to make testing the bridge a lot easier, because that flat area will give you a place to stack items on top of it. So now that we have our bridge design, the first thing that we want to do is identify the parts of the bridge that will need the longest spaghetti lengths. Break 2 pieces of spaghetti into the lengths that you need. For the bottom of my bridge, the spaghetti didn't need any breaking. For the top, I had to snap it to the right length, and I found that the easiest way to do this is to lay it down on your template and then press down pretty hard with one finger exactly where you want the pasta to break. And then just lift up quickly on the other end of the pasta with your other hand. This will help you break the pasta exactly where you need. The next thing you want to do is slide your marshmallows onto the long pieces of pasta by poking the pasta right through the middle of the marshmallows. Just like the pasta is going to represent the straight parts of the beam, the marshmallows are going to be used to represent what we call the joints, or where all the straight pieces meet each other. Every time you see lines connecting with another line, you're going to want to put a marshmallow there. I used a marker to put a dot right at the place that I wanted my marshmallows to go, but you don't have to do that. For the 2 long spaghetti noodles on the top and the bottom of your bridge, you can just slide them on and then adjust your marshmallows once they're on by comparing your marshmallow placement to the truss template. This is what it should look like when you're done. Okay, now that we have all of the marshmallows on our main beam, it's time for us to finish up the rest of the walls of our truss. Snap off enough pieces of pasta to complete the interior, vertical, and diagonal portions of the truss, and then attach them to the marshmallows. Your truss wall will get more rigid as you build it, so as a general rule, I like to attach my supporting pasta noodles starting at the center and then working out to the sides. You can always use your template as a check to keep your connections straight. Okay, that looks pretty good. I'm going to speed up the footage while I build another identical wall for the other side of the truss. Alright, and now that we've got 2 walls, it's time to build a framework to connect them in 3D. You get to decide how wide you want your truss to be, and bear in mind that this is going to be somewhat informed by the things that you have around your house to load the truss. Your truss needs to be wide enough that it can support the objects that you're planning on carrying. But since I am planning on using rice and cans, I think I'm just going to make mine the width of the truss so that I can reuse this template, and I'm just going to keep the same X pattern on the top and the bottom connecting walls. Okay, so now comes the hard part. We need to attach our truss in 3D. So take all these side connecting pieces and just do your best to stick them into the marshmallows at a 90-degree angle, and just do your best to keep everything straight. If it's not perfect, that's okay. You can always go back and fix it. But I like to just try to hold everything steady with one hand while I operate the marshmallow and the noodle in the other. And I promise that this gets easier after the first couple. Okay, when you're all done, it should look a little bit like this. So something that I've noticed that affects the strength of the bridge is how fresh your marshmallows are. So if you have like a really fresh pack of marshmallows, they'll be a little softer, which makes them super easy for putting everything together, but it may make your bridge like a little bit soft and squishy. So if that's happening to your bridge, don't worry about it. All you need to do is just make sure that your bridge is standing up straight, and support it with a book or whatever if you have to, and just let it dry out for a little bit, and when you come back to it, your bridge should be a little bit stiffer. Alright, we've got a bridge. Let's go test it. Alright, now we're going to talk really quick about what you need to build your testing apparatus once we've finished our bridge. So just take a look around and make sure that you're able to create 2 towers of about the same height. And these towers can be made out of anything sturdy. So I tried it with a couple different materials. I tried making them out of books. I tried making them out of cans. And I tried making them out of Tupperware, and all of those things work just fine. The only thing that matters is that they need to be at least a couple inches high, and you need to be able to move them horizontally to a distance of about 5.5 inches apart. So in order to know that you're setting your towers 5.5 inches apart, you can of course measure them with a ruler, which is just fine. But another trick that you can use if you don't have a ruler is just take a regular sheet of paper, because the regular paper is sized 8.5 by 11 inches, and half of 11 is 5.5. Now that we've got our testing apparatus all set up, the only thing left to do is put some weight on this bridge and watch it break. So in the engineering world, there are plenty of competitions that involve building the best bridge, building the best tower, and then breaking those things. So once you've been around that for a while, you understand that there are a couple different ways to load model bridges. One of them is called continuous loading. This is where you suspend a bucket of sand and then you continuously pour the sand into the bucket, and you measure very precisely how much sand is there, and then at the end of it you get a really precise measurement as to how much weight your bridge could take before it failed. So that would be an ideal situation that we would do at the riverfront if we were able to put on a regular Engineers Week for you guys. But because I'm guessing that most of you guys don't have 5-gallon drums of sand lying around, and also probably would not appreciate the mess that would come from that, I'm going to suggest that we do something called discrete loading, which is a little bit more useful in the home setting. So discrete loading means loading one piece at a time. So what it means for us is that we're just going to stack things on top of our bridge until it fails. So this is what I did because I didn't want any rice or sand or anything to spill out into my apartment when my bridge finally failed. So a couple tips for this. So when you're stacking things on top of your bridge, first of all, you might want to think about your base, and you might want to try to put your bigger items on the bottom so that it's easier to stack. Something that's very important is you don't want your bridge to twist too much, so you have to stack it as close to the center as possible. You should load everything very carefully. If you drop your material accidentally onto the bridge, you don't want that extra force to cause the bridge to break early. Another thing that you want to make sure that you don't do is you don't want to accidentally press down on the bridge as you load. So as I'm placing my can, I don't want to be pushing down with my hand. Just come at it from the side and very gently put your can on top of it. for safety, be sure not to put anything breakable or anything that's so heavy that it would damage something else when it falls, and also move anything valuable or electronic away from the bridge so that it doesn't fall on it and break it. So the footage I'm playing you right now is of the brown truss, and that's the one that we did in the demo. What I'm doing right here is I'm just taking a little flat marshmallow and I squashed it down and I set it under the legs just to make sure that they were like nice and stable. I immediately started noticing that my bridge was a little bit wobbly. It either needed some more supports, or sometimes if your bridge is wobbly, you can let your marshmallows dry for a while. And if you want it to be super stiff, you can even let them dry for several days. Okay, so I just keep loading it for a little bit. So I'm just going to speed up so that we can see the fun part. Okay, you guys can probably already see what's happening. My marshmallows are a lot softer than the spaghetti noodles, and so my bridge is starting to fail at the joints, and that's why you see this like bending, sort of melting motion. And what you can't see from this angle is that my bridge is a rectangular shape if you look at it head on, if you look through the truss, and that shape was beginning to twist out of its rectangle and flatten down to the side. So when you see me stick up my hand like this, I'm just literally holding the can and the rice in place so that they continue to push downward on the bridge rather than just fall off. Okay, here you can see it from a better angle. Okay, so I have a confession to make. I did not just make the brown style truss. I also made a second truss called the Parker style truss, which is a slightly different shape, and I also made it out of angel hair noodles rather than spaghetti like I did with the brown. And then the other thing that I did with the Parker truss was I let it dry for several days, somewhat by accident. And so when I actually got around to testing this bridge, all the marshmallows were like super rock hard. And all of these factors kind of came together and they made my bridge fail in a completely different way. So I just want to show you guys the video so you can see what a big difference all of these different factors could make in your bridge. And one more time. Okay, so the Parker Bridge actually, in comparison to the Brown Bridge, was really, really stiff. Remember, the Brown Bridge failed on its weak joints, but the Parker style truss failed because the pasta actually broke first. But we can do one better than this. In the Parker video, we could actually see where the first piece of pasta snapped. Yeah, and right there. So if we know how to analyze our truss, we can actually check whether that specific piece of pasta was supposed to be in tension or compression, and then we can even see how much of the total load it should have been carrying. Okay, so you may be thinking, what is she talking about, analyze your truss? Well, you can actually analyze a 2D truss at home for free on the internet using any number of truss analyzer tools. Some of them are easier to use than others because they're all designed by really technical people, I think. And so this is the one that I like the best, and I think that it's the easiest to use. Okay, so here we are, and this is what the Valdiva staff page looks like. So what I did was I just typed in truss bridge calculator on Google, Valdiva staff jade, right here, the second one, clicked in, okay? You can read the stuff up here, but you come down here basically, and then you start off by just working left to right. I'm gonna put in my points, so just hang tight. And I calculated these off of, I printed off a Parker truss on a piece of paper, and then I just measured using a ruler, so this is what I'm getting them from. They're rounded, but that's okay. Okay, that looks good. All right, now we will go to the next tab. All right, and this is asking us to collect the nodes, and I really like this one because you can just draw. Some of the other ones don't let you do that, but this is a really nice feature. Oh, you know what? Actually, I made a mistake because I have 2 nodes here. So I need to get rid of that because look, I've got 10, 0, and then I've got 10, 0 down here. Not supposed to have that. Okay, so that worked out. Okay, and I'm just looking at my picture just to make sure that I'm drawing the right ones. Okay, there we go, 1 Parker bridge. Okay, so then you would go to this materials page, and this A and E, A stands for cross-sectional areas, so that only really matters if our beams were different thicknesses, but we're just going to say that they're all made of spaghetti noodles, which are all the same. So since we don't care about that, we'll put 1, and then this E is a stiffness value, so again, it's all about the beam material, but we don't care because our spaghetti is all made of the same thing. Okay, so then now we have to do loads. Okay, ooh, so we get to load this up, and I'm going to put down some Y loads, and they're all going to be pointing down, so we'll put that as a negative, okay? And these numbers are going 1, 2, 3, 4, 5, 6, 7, and that's 1, 2, 3, 4, 5, 6, 7. It all corresponds with the node points. Okay, so I'm just going to do -10 across the bottom of my truss for starters. And then you got to go to supports and just on this first one, check X and Y. And then on whatever node is your last node over here, just check Y. All right, and then we'll look at our results. Ooh, so it even shows us the deflection. And yep, this makes sense because in our bridge, we had a lot of load on the bottom. So what this is telling us is, since it's in blue, this is going to be a tension member, and since this is in red, this is going to be a compression member. And then you can't see it too well in here, but these other ones will vary in gradient from red to white to blue. Zero force members, which means that there's no force at all in the bridge, are white. So it's basically showing us that almost all of our weight or all of our force is being held in these outer beams, which totally makes sense. All right, so I want to just try one more thing because we didn't really load our bridge from the bottom. We really loaded it from the top. So I'm going to load up 9, 10, 11, and we'll see what that does. Oh, okay, see, this changes things. And you can see there's slightly different shading. So this is darker blue than over here. And these are still showing us that they're tension members. And this is showing us that this is a little bit of a compression member here, but not too bad. And it looks like we have some true zero force members over here. So if you look over here, you'll remember that we didn't put in real loads. I just put everything as -10, even though I don't really know what it could be. And we also didn't put in a cross-sectional area. So these don't show the real forces, but we can still learn something from looking at these results. So we can tell like beam 3 and 4 are going to carry an equal amount of load. See? And then we can also tell that 3 is going to carry a bigger load than 2. And we can see because 3 is darker than 2. And we know that blue is tension. And so the positive sign here is tension 2. So this is another way that you can check. Okay, let's take a look at our Parker Bridge and remember where it failed. And I think it was right here on this section. And that makes perfect sense because this is one of the darkest sections in the entire bridge, which means that it's under the most force out of all the members in the bridge. So if our bridge was going to fail anywhere, it was going to fail right here, exactly where we would expect it to. Thanks for coming, everybody, and have an awesome Engineers Week.